So till now we have discussed about the evolution of power system, and then we discussed about the evolution of power system automation, and then we also saw that how the information technology, communication network, and the computer networks were evolved in the past. We also discussed that the power system network was quite matured by 1970, and by that time the information technology and communication technologies which we are seeing today were not existing. So because of that, the integration of these technologies were not happening in the power system network. Different technologies were developed in silos, and there was no integration of those technologies in the power system network until we started realizing the concept of smart grid. So now let's try to first understand the existing structure of power system network so that we can understand what is the difference between what we have right now and what we want to achieve in terms of the smart grid technology in the future. So let's see the existing structure of power system network. So uh, before going into the structure, let's see how the growth of our power generation happened in the past. So when we got independence on 15th August 1947, by December 1947, we were having only 1362 megawatt of power generation capacity. And then later on, through various years, we increased our power generation capacity, and by 31st March 2019, we increased up to 356 gigawatt. So you can see that on the average, we are growing at the rate of say 5 to 6%. And the latest data is that by July 2020, our power generation has increased up to 371 gigawatt. Now, in terms of electricity production, where we stand in the world, so you can see that China is the leader in the electricity generation. So China generates around 6 million terawatt hour units, and then second is United States. We are third. So you can see that when you compare with China and United States, our electricity production is very less. So when we modernize the other industries, that is your production industry, IT industry, or financial sector, or and so on, your demand for the electricity generation will keep on increasing. So you can see that as of now, although we have reached up to 371 gigawatt, but this may not be sufficient for future. So we have to keep on adding more power generation. Now let's see how we generate and transmit and distribute power. Conventionally, what we do, we have one power plant where we generate electricity, and it generally happens at say around 11 kV or 12 kV level, and then using your step up transformers, we increase it up to 750 kilovolt. That is the nominal transmission capacity which we have achieved right now. We are also trying to reach up to 1200 kilovolt. That is still under pilot phase. So now we transmit the power to the distribution end. So at distribution end, you again convert it back to the medium voltage and high voltage distribution level, that is 66, 33, and 11 kV, and then you reduce further to 440 volt for end consumer. So this is how you send power from generating station to transmission and then the distribution network and at the home level. Now these homes are metered, so you calculate the energy consumption and you bill them accordingly. At distribution level, you may have the medium voltage customers also, where you send power at 33 kV and 11 kV. So, for example, IIT Kanpur is in medium voltage customer level because we get power at 33 kV. We have 33 by 11 kV substation near SVRA. So there we convert that power from 33 to 11 kV, and then the power distribution happens at 11 kV to various distribution substations which we have in the campus. So in campus we have 10 distribution substations which convert 11 kV to 440 volt, and then that 440 volt is being supplied to various loads. So this is the traditional way of sending power from generating stations to the load end. Now, how you monitor and control the power at the transmission level? So we utilize supervisory control and data acquisition system, that is called as SCADA. How it is structured? So let's see the architecture of the SCADA system. At the substation level, we have a device called remote terminal unit. We also use PLCs, that is programmable logic controllers. These devices are utilized to sense the various parameters, say voltage, current, frequency, and so on. So those are received in analog values to the RTUs. RTUs convert it into digital format, and then using digital communication protocols, the data travels using the wireless or wired network to the control center. At the control center, what you will have? At the control center, you will have one local area network, which is generally called as a SCADA network because all the SCADA related devices are connected to that network. So what we will have in that network? The routers will be connected to that bus to to get the data from RTU to the server, and you will have one database server which will store the information coming from RTUs. We will have an application server where SCADA application will be running. We will have OPC server. OPC is nothing but OLE for process control. That is open source protocol utilized for SCADA data communication. So we'll discuss in detail when we talk about the IC 60870-5-101 protocol. So there we'll see how OPC and 101 are different. So this server is required because the protocol level data communication has to be handled. Now HMI is nothing but human machine interface, where operator sits and sees the single line diagram of the power system network that is being integrated with the data which you get from RTU. So RTU data will be displayed on the human machine interface display, where operator will keep on seeing the change in voltage, current, and various parameters, and then accordingly the operator will take actions to save the system for any abnormal activities. Say if the fault happens, operator can initiate command which goes back to router and then back to RTU to send command back to the relays, so that relay can operate and isolate the network. So this is how the SCADA system is structured in the power system network for monitoring and control using software applications. Now this is the SCADA system which you will see normally at one control center, but in countries like India, where the power system network size is very large, then how you will handle this SCADA communication? So there you will have different hierarchies. So at the end you will have RTUs, or maybe intelligent electronic devices, or maybe programmable logic controllers. So at the base, at every substation, you will see the devices which are connected. They keep on sending data to the sub area local dispatch center, which is nothing but the first SCADA control center, where RTU data is aggregated and the local area display is seen on the human machine interface. So this is the area which is being monitored and controlled by the SCADA application installed in this control center. Now, this control center size may be small, maybe the scope of this SCADA is only a city, or maybe one or two suburbs. Then how we will realize the complete district or maybe the state? Then these multiple sub LDCs will send data to state load dispatch center. That means at a state level, the data of complete state is aggregated and the state level information is monitored and controlled at this level. Now, from SLDC, the data goes to RLDC, that is Regional Load Dispatch Center. In India, we have 5 RLDCs, that is Regional Load Dispatch Center. So we have Northwest, South, East, and Northeast Regional Load Dispatch Center. So in North Regional Load Dispatch Center, we have 8 states, including UP, Uttarakhand, Delhi, Haryana, Punjab, Jammu, Kashmir, Rajasthan. So that RLDC will aggregate the data of all those states which are falling under that RLDC. Then the data flows to National Load Dispatch Center, that is the nation level visualization SCADA platform which we have in Delhi. So at National Load Dispatch Center level, the data related to the complete power system network of a country is seen. So you can see that how hierarchically the data travels from RTU to the National Load Dispatch Center level. Now at every stage you will see time delay is being added. So when RTU adds data, then it sends data to LDC, will take around 10 to 20 seconds. Then from sub LDC to SLDC, again 10 seconds delay will be there. From SLDC to RLDC, the again 10-second delay is there. And then to NLDC, again 10-second delay will be added. So you can see that in this particular hierarchical process, you add around 40 to 50 seconds of delay. So at NLDC level, if one event occurs here, the effect will be seen only after say 1 minute. So this is a major challenge in the conventional way of SCADA data communication, because if you remember on 30th and 31st of July 2012 we had a blackout, and the healthy to blackout state achieved in just 3.5 seconds. So now you can understand that if you are not able to visualize or see the change of the power system network in just a small fraction of time, it is very difficult to avoid the blackouts. So in the next video, we will discuss again in detail about the various roles of these agencies, so that you can get better insight about the detailed structure of the power system network for data communication which we have in our country.